Hello mates, in the previous video we were just continuing with the examples, and I said there's an interesting one called the vertical circle situation, and I wanted it to be a video on its own because it seems like a section on its own. The vertical circle, it has considerations that are very important. So let's explain the situation. The situation is like this. Let me draw it and then I'll explain it. Consider this to be a vertical circle. So it's vertical. We're just looking at it from the side. It's a vertical circle. And here is the center of the circle. So now we have a ball of mass 150 grams on the end of a 110 long cord swinging in a what? Or revolving in a vertical circle. So this one, the radius will be equal to 1.1 meter long rod. If you cannot understand what I'm saying, or if you cannot get the questions properly, just download my PDF. All of these examples that I'm doing are there in my PDF, and I'm actually going to leave one out for you to just see on the PDF. The last example is just there on the PDF. I'm not going to do it on a video. So yeah, this is the situation. They're saying this ball is attached to a rod that is of length 110. So I have automatically called it the radius because that's the length of the what of the rod. The part A is saying determine the minimum speed the ball must have at the top of its arc, so that the ball continues to move in a circle. So you know when something is rotating in a circle, here it will have the greatest speed because it is falling. As it is falling, it gains speed, right? And then it goes whoosh. But then when it starts going up, it then starts losing velocity. As it is losing velocity, sometimes you might even fall back like this. But we want to make sure that it continues moving in a circle, so we need the minimum velocity that it has to have when it gets to this point, so that it continues moving in a circle, so that when it gains a lot of speed, when it starts losing, if it reaches this point with a minimum velocity, it is able to continue moving in a circle and not fall back. So that's the minimum velocity that we want for part A. And part B is saying calculate the tension in the cord at the bottom of the arc, assuming the ball is moving at twice the speed of the part in A. So here this is what part A, and part B is considering this point. We want the tension in this part. Here we want the minimum speed. So here we need the speed. Here we need the what? The tension. Let's jump right into it and explain what is going on. So in a vertical circle, the ball doesn't go uniform circular motion. That is very important. In a vertical circle, it doesn't go through uniform circular motion. You know, when uniform circular motion is in, it doesn't go through, with the uniform speed. Speed changes as it is falling, and it also decreases. Speed decreases as it is increasing against gravity. So the speed is not constant in a vertical circle. Here it's increasing as it is in the same direction as gravity. It's in the same direction as the force, so speed increases. Here it's in the what? In opposite direction to the force, so it's retarding. It's what? It's decelerating. So so that is very important. The speed varies due to what? Due to gravity. Point number 1: two forces act on the ball. So here we're going to consider two forces. Let's consider this situation here, and then we'll consider this situation. At this situation here, we know that there are going to be two forces that are acting. We have the weight, and we are going to have the tension in the cord. Weight, W, is equal to mg. From Newton's second law of motion, it says F is equal to ma. The force is going to be the weight, and the acceleration is going to be acceleration due to gravity. And the tension is going to be equal to T. So we are going to represent the weight as mg and the tension T. So at this point, you are going to have mg facing downwards because it's always facing downwards. And if you remember, if you're following through this as a series, you remember that the tension is always facing the center like this. It's always along the what? It's always along the cord facing the center. That is the situation at this point. mg is facing down and the tension is facing up. At this point here, something interesting happens. mg always has to face downwards towards the ground. It has to face towards the ground always. And the tension, what happens to the tension? The tension is always along the string, but facing the what? the center. That's what happens to the tension. It's always facing the center. So at this point, they are both facing the same direction, and in this case, the two forces are facing opposite directions. So that is a very, very important point. At the bottom, they are facing opposite direction because mg has to face downwards, and tension has to face the center, so they are in opposite directions. But here they're in the same direction because tension always has to face the center, okay? And mg has to face downwards, so they are now facing what? The same direction. So now we are going to choose the bottom direction. Okay, this is just for convention, for it to be easy to calculate. Choose what? Downward as positive. We're going to choose the downward direction as what? As positive. As positive. That's what we're going to do. We're going to do what? To choose direction. The direction downwards as what? As positive. So here let's call this tension. Let's give this tension different symbols for it to be easy for us to reference them. So this tension here will be T1, and this tension, let it be T2. Let it be T2. So this tension T1, T2, the weight does not change. That's going to be mg. So let's look at the different situations. At point A, at that point A, at the top here, can you see both of them are contributing to the what? To the centripetal force, because both of them are facing the what? The center, and this small object is moving in a what? In a circle. So we know that our resultant force is equal to ma from Newton's second law of motion. Our resultant force is equal to ma, but since they are both facing the center, as we can see here, they're both facing the center, it means the resultant force will be T1 plus mg, because they're both facing the same direction. So T1 plus mg is the resultant force, and it is equal to the centripetal force because both of them are facing the center. So this is equal to m, and this is equal to ma, but a is equal to v squared over r. We know that a is equal to v squared over r, right? That is the calculation of a. At this point here, it's going to let the velocity at this point here be v1. Let the velocity at the top part be v1. So which means the a is going to be equal to, at this top part a, is going to be v1. So the acceleration at the top part is going to be v1 squared over r. So this centripetal force will be mv1 squared over the radius r. So that is one equation that we have come up with. The v1 being the velocity at the top. We know that the velocities are going to be different at the top and at the bottom. So T1 is large if V1, as you can see here, T1 is large if V1, the ball at the steep, at the top here, is large. So we've come up with the what? We've come up with that situation. Sorry about that, mates. I think you will see a glitch in the video, like the flow of the video. It's because I shook my camera, and then since I use a CD to record, you know, a CD, when you shake it, it doesn't flow so nicely. We're considering an example of a vertical circle. So this was a vertical circle, and now we had come up with all of these conclusions about the situations, the situation at A and the situation at B. B being the lower point and A being the top point. We said we're looking at the top point first, because the question A is asking us to find the minimum velocity that this ball needs to have when it gets to A, so that it continues moving in a circle. And I'd said if it gets to this point without that minimum velocity, it's going to fall back. Although it was moving like this, if it doesn't have that initial that minimum velocity, it will fall back, and then it will just do something like this and then rest here. But we want it to keep going, so it means it needs to get here with a minimum velocity after fighting gravity, as it is going up like this. So as it fights gravity, it loses velocity because it's going against gravity, is going against a force. So as it is going against a force, it starts losing velocity, but it should get to this point with a minimum velocity that is just enough for it to pass this point of fighting gravity, and then gravity assists it as it is falling down on this path. So as it's falling down on this path, it means that its motion is now in the same direction as force. So here it will gain velocity. It will start gaining velocity, and the maximum velocity will obviously be here because it has fallen the maximum distance. And the moment it passes here, it now starts what? Losing velocity, as it is what? Fighting gravity again. As it fighting gravity, losing velocity, and it's supposed to get here with the minimum velocity that just allows it to just pass this point of fighting velocity to what? To being aided by velocity. I hope you understand that. So that's that v1. That v1 is that minimum velocity that we need to calculate at this point. That's that v1 that I put there. So this v1 is the one that we are calculating. At this point A, we consider the forces that are there, because the forces that are there are going to give us the centripetal force. The centripetal force being the resultant of this force, of the forces acting at a point. We know that there is the centripetal force is going to be the resultant, because this thing is continuing in a circle. That is the assumption that we're using, that is continuing in a circle, which means there has to be a resultant force that keeps it in a circle. So we looked at the forces at A. We saw that the tension is always center seeking, so it will be facing down. But weight mg is always facing down, no matter where it is, even if it's here, it's always facing down. So these are the forces, and they're all facing the center. As they are all facing the center, they are both contributing to the what? To the centripetal force. So here, this is just the resultant. Even when I don't put this summation sign, I'm basically saying the resultant force at any point is equal to ma by Newton's second law of motion. But at A, can you see they are both facing the center? So T1 plus mg, the tension force plus the weight force, they are the ones that are being the resultant force, because there's no other opposing force. We have accounted for all the forces that are at A, the tension and the weight. So T1 plus mg will be equal to ma. But A is equal to V1 over R squared. Coming from A is equal to V squared over R at any point. But at our particular point A, our velocity is V1. So our A is V1 squared over R. So that's where we were when I shook the video. So we are going to continue from this part. So from that part, we need the minimum velocity. So we need to calculate V1 so that this thing continues in a circle. The minimum velocity occurs when the tension is zero. This makes a bit of intuitive sense. Okay, when I explain it, we explain it like this: the tension at this point, the chord at this point, you know, the tension is directly proportional. Let me just loosely say tension is directly proportional to the tautness of the chord. Is proportional to the tautness of the chord, or the stretching of the chord. The stretching of the chord is directly proportional to what? To the tension, the stretching of the chord. So if the tension is maximum, then the chord is stretched out to the max. It's stretched out to the maximum. If the tension is half, then maybe the chord is not exactly what? Is not exactly stretched out to the maximum. Maybe it's just lacking like that. If the tension is zero, then the chord is not even. It's not even being stretched, because the tension is zero. There's no tension in the chord. So that's the point. So when there's no tension in this chord, it seems as if this ball just went up. When it got there, it lost all the tension, because it does not have enough velocity. Can you see here? Tension is directly proportional to velocity. So as the velocity increases, the tension also increases, isn't it? The tension also increases. As the velocity decreases, the tension also decreases. So there is a point where to reach where the velocity will be so low that this tension will be zero. It means now this ball is not going to move in a circle. The tension is not zero, so it's going to what? It's going to not have taut. It's not going to be taut. It's going to be loose. When it's loose, then it stops moving in a circle. So we want that exact point where it loses what? It loses the tension. Where it just loses the tension. If it just loses the tension, we want that point to be at the top, because if it just loses tension at the top, when the T1 is equal to zero, it doesn't matter much, because now gravity is aiding it, and then the velocity will start increasing. When the velocity starts increasing, by this proportion, tension will also start increasing. So if that point when it's losing tension, when it starts losing tension, you want the tension to just be zero at this point, at this top point here, because when it gets to 0, this ball will be like, oh, I've lost tautness, I'm not supposed to fall down, but it will not fall down because gravity will say, no, let me help you, and then it will continue, and then the velocity will increase, the tension will increase. So this top part here, that's where we want our tension to just be 0. So at the top part, let our tension be 0. So let T1 equal to 0 newtons. I hope you understand that this only occurs, this is not on, this is 0 newtons. 0 newtons. So we want it to be 0 newtons just at the top part. If it was 0 newtons at this part, if it was 0 newtons when the ball was here, and then it stops being taut, it just then loses tension, it becomes like this, then the ball will fall. But if it loses tension just at the top part, instead of falling, gravity will then aid it to go in that direction. Gravity will then make it fall in that direction and increase velocity and thus increase tension. So this is the part where we want our tension to just be 0. So at the top part point A, let the tension be equal to 0 newtons. So this is the situation. T1 is equal to 0 newtons. But when T1 is equal to 0 newtons, this is 0. So my mg is equal to mv1 squared over r. These m's can cancel, isn't it, using algebra. Therefore, my v1 squared will be equal to gr, which is equal to, so therefore, which implies that what my v1 is equal to, which implies that v1 is square root of gr. G, if we use 9.8 multiplied by, we already know the radius, we're told that it's 1.1 meters. It's 1.1 meters, isn't it? So now we can calculate that minimum velocity that gives that tension of 0. That will be equal to 3.28 meters per second. Like that. So this velocity, if it gets to the top part with that velocity, it's just going to lose tension at the top, just right there at the top part. It's going to just lose velocity, tension at the top part. But because it's the top part, the gravity will start working again, and then it will gain velocity. So this is the minimum velocity. The minimum velocity is v1 is equal to 3.28 right there at the top part. I hope you understand my explanations, because this is a very interesting situation, and many examiners like the vertical circles. That's why I had to make it a separate video on its own. The question B is saying when the ball is at the bottom, when the ball is at the bottom. Okay, we want the tension. We want the. Let's see the question again. The question was asking. Calculate the tension in the cord at the bottom of the arc, assuming the ball is moving at twice the speed at the top, at the part B or part A, I mean, or at the top. So when the ball is at the bottom, the cord exerts tension T2 upwards. You remember from our drawing here, the tension was T2 at the bottom. We called it T2 just to differentiate from T1, because they are not going to be the same tensions due to the different velocities. So T2 here, that's the situation at the bottom. So let's use our what? Let's use our Fr is equal to Ma. Can you see that the tension at the tension T2 is facing up and T1 is facing and Mg is facing down, which means there's what? There's going to be subtraction of the forces. But which force is going to win? T2 is going to win the subtraction, because this thing is continuing in a what? In a circle. So if it's continuing in a circle, it means the top forces are greater than the bottom forces, because if the bottom forces were greater, it was going to fall, the ball was going to fall, but the ball is not falling, it's continuing in this part, which means these forces on the top part are more than the ones at the bottom. So we're going to calculate our resultant. Resultant will be equal to T2 minus Mg. The subtraction of this will give the resultant, but the resultant is equal to what? To mv squared over r. mv squared over r. And the velocity at the bottom, I called it v2. If you remember from the what? From the diagram, the velocity at the bottom, I hadn't said anything, but the velocity at the bottom, I'm going to call it v2. And it's different from v1, because as I keep explaining that the velocities are different in a what? In a vertical circle. So this one is going to be v2. So that one is going to be mv2 squared over r. But we are told a very interesting part. v2 is equal to twice the velocity at the top, 2v1. So this is 2 times 3.28, which is equal to 6.56 meters per second. So that is v2. So already we have our v2, we have our r. So now we can calculate our tension. Therefore our T2, making T2 the subject of the formula, it's mv2 squared over r plus mg. This will be equal to 0.15, because we have the mass, times v2 we've calculated at 6.56 squared over the radius, which is 1.1, plus m, which is 0.5, and our g, which is 9.8. So this will give us an approximate tension of 7.34 newtons. So that is the tension at the at the bottom when it's moving at twice the velocity of what? Of the top part. If it was 3 times the velocity, you just put 3 and calculate the new tension. It was 4 times, how many times, million times, you'd get the new tension. So that's basically what a vertical circle, and it is a very, very good example of showing you how situations differ when the object is moving in a horizontal circle or a vertical circle. I hope you understand this example, and if you have any questions, just don't be afraid to ask me. I'll be glad to explain further this concept. And in my PDF, there's an example after this one of a banked road. You can download the PDF and go over that example. If you do not understand it, just contact me and I'll explain it to you, and I'll give you more examples, more circular motion examples. I hope you enjoyed this section of circular motion. In the next part, we are now getting into a different topic. So stay tuned for that topic. You're following this as a series. I hope you have learned a lot. Just keep in contact if you have any questions. Thank you.